Good morning, students. In our previous lecture, we were discussing related to the Nernst equation, which was used to calculate the cell potential for the non-standard cells. Today we will do some of the numericals based on it. Right? Using Nernst equation, we will try to solve some numericals. Like the first numerical that is given to us, a voltaic cell. Is set up at 25 degrees Celsius. At 25 degrees Celsius temperature with the following half cell. The cell reaction is given to us Ag plus, that is 0.001 molar Ag, and Cu plus 2, that is 0.01 molar Cu. These were the two half cells that were being used. It's given to us what will be the question is asked to us, what will be the cell potential if the standard cell potential of the half cells are 0.80 volt and 0.304 volt respectively. That means it's given to us on anode, we will get it as Cu getting converted into Cu plus 2 plus 2E, that is oxidation is going to take place, and we know it that because the two potentials are given to us, E naught of Ag plus Ag 0.80, E naught of Cu plus 2 Cu, it's a 0.34 volt, right? And we know it that whose potential is more will act as cathode. Now this is reduction potential, it's a plus 1 to 0, it's a plus 2 to 0. So in both the cases the reduction potential is given to us. Whose reduction potential is more will act as cathode, whose reduction potential will be less will act as anode. So here reduction potential is less, so it acts as anode, and on cathode the reaction we will be getting it is Ag plus plus electron gets converted into Ag, that will be reduction potential, right? Okay, now the reactions are not balanced. The reason is it's losing 2 electrons while it's gaining only 1. So it is necessary that we should balance it. So this whole equation, if I multiply it by 2, we get it as 2Ag plus 2E gets converted into 2Ag. Now the reaction is balanced, right? So that is a must. So net reaction we are going to get it as Cu 2Ag plus gets converted into Cu plus 2 plus 2Ag. Now concentration of Ag plus solution is given to us, and for Cu that means both of them are in non-standard condition. Both of these are in a non-standard condition. So it is necessary that we should calculate the cell potential for non-standard by using Nernst equation. But then in that case, given to us anode cathode are given, reactions are given, potentials are given. So first factor that I will be calculating it is, in this sum what I will do it is, first of all we will calculate E naught. In this sum, we will first of all calculate E naught. E naught cell is equals to E of cathode minus E of anode, standard condition. So we will get it as 0.80 minus 0.34. That means we will get it 0.46 volt. That is the E naught of the cell. Now, according to the Nernst equation, we are going to write it as E cell is equals to E naught cell minus 0.059 by n log of anode Cu plus 2 cathode Eg plus, right? So in this case what will happen? According to the reaction, X was 1, while for Ag you will be getting it as square for it, right? So what is the cell potential that we will be getting it? E cell, that is equals to, this one we got it 0.46, right, minus 0.059. Electron transfer during the reaction, that we saw it loses 2 electron, it gains 2 electron, so 2 log of, we will be getting it log of 0.01 upon 0.001 whole square, right? The reason is we got it here 2 multiplied for it. So E cell is equals to 0.46 minus 0.059 by 2 log. This one will become 1 into 10 raised to minus 2, and this is 1 into 10 raised to minus 3 whole square. So 1 into 10 raised to minus 6. So if we find out the answer, we will be getting it as 0.46 minus 0.059 by 2 log 1 into 10 raised to 4. This one will become 4, so this is cancelled out. So we will get it as 0.46 minus 0.059 into 2. Calculate the answer and get the answer for these. It's a E naught cell, 0.46. That will become as a minus whatever the answer we get it, 0.059 into 2. That will be your cell potential. Okay, this you can do the calculation by yourself. Okay, now this was your first sum, where we saw it that why the stoichiometric coefficient of balance reaction is necessary to be written, right? Otherwise these exponential factors, that will make an error and our whole calculation will become wrong. So for this, first of all, anodic and cathodic reactions are necessary to be written. Okay, let's take one more numerical. A galvanic cell is constructed. With Ag plus Ag and Fe plus 2 Fe. Fe plus 2 Fe electrodes. Find the concentration of Ag plus, at which the EMF of the cell is 0. At equimolar concentration of Fe plus 2 and Fe, here it is given to us Fe plus 3 to Fe plus 2 and Fe plus 3 ions. it's given to us E of Ag plus Ag, that is equals to 0.80 volt, and that of Fe plus 3 Fe plus 2, that is 0.77 volt. Now this much is given to us, right? And they are asking us calculate the concentration of Ag plus solution. So first of all, from this, can I say that this one will act as an anode, cathode, this one will act as an anode, its reduction potential is less, more than Fe plus 2, Fe plus 3 to Fe plus 2. So Fe plus 3, Fe plus 2 is going to act as anode. So can I write it? Anodic reaction, anode will get it as Fe plus 2 gets converted into Fe plus 3 plus electron. And on cathode, we will get it as Ag plus electron gets converted into Ag. In this reaction, one electron is donated by Fe, one electron is gained by Ag. So balanced reaction is there. So net reaction, we are going to get it as Fe plus 2 plus Ag plus gets converted into Fe plus 3 plus Ag. This is your net reaction. Now let us go it for, these are not in the standard condition. It's told to us Fe plus 3 and Fe plus 2 are of same concentration. So according to this, the Nernst equation first of all will be required to be written E naught cell minus 0.059 by n log of. Now here the log we will be getting it of Fe plus 2 upon Fe plus 3, that is anode, that is for anode, plus 2 to plus 3 into, we will be getting it as an cathode as Ag plus Ag, but we know it, this is in the solid condition, so its value is going to come out to be as 1. These are the equimolar concentration, and when we are saying it as an equimolar concentration, that means we will be getting this value as same, so they will be cancelled out. So we will get it as E naught cell minus 0.059 by n log Ag plus, the equation we will be getting it as E cell is equals to E naught cell minus 0.059 by n log Ag plus. Now let's calculate E naught cell. E of right minus E of L, that is cathode anode. So we will be getting it as 0.80 minus 0.77, that is 0.03 volt. So E cell, we are going to get it as 0.03. It's in the equimolar concentration. So this cell potential, it's told to us EM of the cell should be 0. So this value should be 0. This is 0.3 minus 0.059. Electron transfer during the reaction is 1 log of Ag plus. Right? So from this, can I write it as 0.03 is equals to 0.059 log Ag plus. Okay, we are getting it as 0.03. If we get it 0.03 by 0.059, that is equals to log of Ag plus. Now this is what we are getting it, log of Ag plus. So log of Ag plus, we will be getting it as 3 by 5.9. Whatever the answer we are getting it. A, we will be getting it as a concentration of Ag plus as anti-log of A. That will be your answer. Right? Find out the anti-log of whatever the answer we are getting it. We will be getting the concentration of Ag plus, at which the cell potential of the cell will become 0.0 volt. Right? Okay. Let's do it. Another sum. Now this time, in place of taking it as a generalized sum, we will take it as one of the specific units that we saw it for the Nernst equation. We will go for the application of its equation. Right? The first application that we studied was to calculate the cell potential of standards, this concentration cell. Cell potential of the concentration cell. So what we will be having it, the question we are having it, determine the EMF of the galvanic cell for the given cell. Determine the EMF of the concentration cell given below. Now cell is given to me Ag plus, this is solid, this concentration is given to me 0.01 molar, aqueous solution Ag plus, its concentration is given to me 0.1 molar Ag. For this cell, we want to calculate the cell potential, and it is given to us E naught of Ag plus Ag, it's equals to 0.80 volt. Right? Okay. Now, according to the sum, first of all, we will calculate the E naught cell. It will be always 0.0. How we got it? According to E cell, E of right minus E of left. Now, for the right, it's a 0.80. For the left also, it is 0.80. So we are going to get it as E naught cell equals to 0. This is one of the question where we will be getting it as an objective question. Where, at what condition EMF of the cell, E naught cell, will be 0 if the given cell is concentration cell. Similarly, under what condition the cell potential of the cell will become 0. Now this time I did not use the standard cell potential. I told only cell potential. So for that case, it's a when the cell is in equilibrium condition, E cell will become 0. So when will be E naught cell 0? Concentration cell. When will be the E cell 0? When the cell is in equilibrium. So this, be careful. Right? Now using this, we got it as Nernst equation. E cell is equals to E naught cell minus 0.059 by n log anode of Ag plus, that is for anode. Again here Ag plus, but that is for cathode. So we will be getting it as, this is 0.059 by n, that electron transfer is 1. How we got that electron transfer? On anode, the reaction we will be getting it as Ag plus, Ag gets converted into Ag plus plus electron. On cathode, we get it as Ag plus plus electron gets converted into Ag. Right? So electron transfer during the reaction is 1. So we placed it n equals to 1. Log of concentration of anode is 0.01, cathode is 0.1. So we will be getting it as 0.0 minus 0.059 log 1 by 10. Right? Log 1 by 10. That means log 1 minus log 10. Log 10 is, we know it, log 10, 1, but it's a minus. So we will be getting the answer as 0.059. Right? Make the calculations for this and you will get the answer. So this is for the concentration cell. Actually, when the electrodes are same, then reaction should not take place. But reaction took place. The reason is its concentrations are different. Though the electrodes are same, concentrations are different. and that is the reason why we got it as some cell potential or certain chemical energy is converted into electrical energy, right? So for this lecture we saw it general Nernst equation, and we also saw it how to apply it for concentration cell. In our next lecture we will see some numericals more, where we will be going it for equilibrium and thermodynamics, how they have been applied. The Nernst equation is applied for equilibrium or for thermodynamics calculation, that is Gibbs free energy or equilibrium constant, right? We will see it in our next lecture. Thank you.